Hi everyone, and welcome to the first of my higher chemistry videos. We're going to be having a look at Unit 3 and controlling the rate of reaction this time. So what we're going to look at today is just building on some of our National 5 knowledge and adding in a few explanations as to why certain factors actually do increase the rate of reaction. Some schools might have this in with the Unit 1 notes. It ties in to Unit 1 from National 5, and some schools will be trying to keep that consistent, so don't get confused. This is formally part of Unit 3, but National 5 rates of reaction was always in Unit 1, so you might find that you do this early on in the course, or you might do it a wee bit later on. So to start off, we're going to have a look at collision theory, and there are two key things that need to happen that are required in order for a reaction to be successful. Now, you kind of knew this from National 5, you knew that our particles have. Secondly, there is the energy that is actually required, and there is a minimum energy, and we'll define this as the activation energy, and we'll be talking a lot about this later on. What we'll have a look at is we'll have a look at this collision geometry first. So I'll do this in two different ways. I will write this down on the sheet of paper. I'll also use a couple of mods just to show you. So if I was going to have a look at an addition reaction, for example, now I'm going to draw ethene. I'm going to draw it in this particular way just now. So from National 5, we know about our addition reactions, and we know that this will add to bromine or bromine water, and that's our test for unsaturation, and the resulting compound will have a bromine on each of the carbons, and then there's no longer a double bond. That reaction will only take place if this molecule and this molecule are in the correct geometry, as in they approach each other in one particular way. So I'm going to say, just for argument's sake, that this is the way that this reaction would work. So if my two substances came together, my two compounds, and I had ethane still like this, but let's say now bromine is this way around. Well, that might not lead to a successful reaction. They're not the correct orientation. Now, just kind of putting that into our molecular model terms. Now, if I have ethene here, you can see there's the double bond using the molecular models. Here's bromine. What I'm saying is that bromine has to approach ethene in this particular way in order for that reaction to take place. That collision will be successful. If it was to come this way, that collision will not be successful, and we will not end up with a desired product. So it must be in the correct orientation. We must have the correct collision geometry, and that's what we mean by that. The second thing is that these have to have enough energy. So you know before, all these particles are always moving around, and in order for them to actually successfully collide, this might be in the right orientation, but if it's moving really slowly, if there's not enough energy in there, there's not enough energy to break the bonds that need to be broken, this one here and this one here, and make the new bonds. So they have to have sufficient energy, and they also have to have the correct geometry. Those are the two factors that are needed for a successful collision, and we need to know these. Still thinking about collision theory, we know that there are 4 different factors which can increase the rate of reaction. This is not new from National 5, so you should be able to tell me that if you increase the temperature, then you'll increase the rate of reaction. If you increase the concentration, then you will increase the rate of reaction. If you decrease the particle size, you will also increase the rate of reaction. That's increasing your surface area, and using a catalyst. Now, the particle size we should already know from National 5, but I'll just put that on the screen just for you to have a wee look at. So if I have a large particle, so what I'm saying here is these solid lines are the edges of my particle. So the edges of that particle and the face of the particle are the only places that those collisions can occur. So those collisions can only happen at those particular sites, at those spaces. If I was to cut along these dotted lines and break up this one particle into smaller ones, all of a sudden, where these dotted lines are, become an outside surface to particles. That is a new surface for these collisions to take place on, and so I have increased the surface area, and I have increased where those reactions and those collisions can take place, and therefore my speed of reaction is increased, my rate of reaction is increased. So the greater the surface area, the greater the number of collisions, therefore the greater number of successful collisions, because remember, not all collisions will have the correct geometry or the correct energy. So if you have more collisions, there's more chance of them being successful, and therefore you have a faster rate of reaction. This isn't really new from National 5. What we do need to consider is our temperature. So for collisions to be successful, they need to have sufficient energy. Here, nice wee animation of slow moving cold particles and warmer, fast particles moving in here. These are not going to have as much energy as these particles, so this is going to have fewer successful collisions and this will have more. But this is new. These are our particle distribution curves, and these actually explain why this is the case. So what I'm going to do is I'm going to move on to the paper and I'm going to draw these out, because having a look at it just on the screen when you've not seen it before might be a little bit daunting. So let's draw one of these out. So please excuse the lack of ruler. Okay, so here are my axes. I'm saying here this is my kinetic energy. Okay, so the energy that those particles have, they are moving around, that's the energy that they have. And up here I'm going to have number of particles. Okay, what we tend to see is that there are some particles that have very little kinetic energy and aren't really moving that much. And this is just a standard distribution curve, and what you find is that there's a particular area in here. A lot of particles will have this energy, fewer will have greater than that. Okay, so if you think about the averages of anything, this is where the kind of average energy would be at the peak of this curve. We've said that you need to have a minimum quantity of energy. Now let's just say we can assign this arbitrary values if we want. Let's say that's 0 and this is, I don't know, 50. Let's put, just right in the middle here's 25. Let's say we have an activation energy of what? 35 maybe? So let's say at 35 kilojoules per mole, this is what we would call my activation energy. So my particles need to have this energy in order to have the correct energy or enough energy to react. That means that all of the particles that have these energies here, so this area under the curve represents that number of particles that has that energy. Okay, the particles represented by this area of the curve have energy less than 35, and therefore they will not have a successful collision. They might have the correct geometry, but they will not have a successful collision. I'm just going to extend this y-axis a little bit just now. This is my first temperature, temperature 1. Okay. If I increase the temperature of my reaction, what I'm doing is I'm giving the particles more energy on average, and so my curve shifts over a little bit to the right. So this is my second temperature, which is greater than temperature 1. Okay, my curve has moved over because more particles have this greater energy now. They all have been given more energy, so it moves over. What that now means is this area under the curve, which I'll just do by these lines, represents the number of particles with the energy greater than this case 35. Okay, remember this is a random number that I've picked out. There are more particles, there's a greater area under this curve than there was in this original one. And so more particles have sufficient energy, therefore there's greater chance of a successful collision, and therefore the rate of reaction will increase. If I were to decrease the temperature from temperature 1, that's going to come up here. It's a really bad curve. But let's then just say that this is the area under the curve that has greater than that energy, that activation energy. Far fewer particles, a much slower reaction. So this is temperature 3, which is lower than temperature 1. Very small area under the curve is above this activation energy now. Okay, so if you're increasing the temperature, this curve shifts and flattens to this side. You have more of that curve above the activation energy to this side of the activation energy, and therefore more particles have the required energy to react. And that is why the temperature, when you increase it, will increase your rate of reaction. Okay, and that is just shown again on the slide. So you can see the two together just now, just talking about at lower temperatures, fewer particles have energy greater than EA, which is activation energy. At higher temperatures, the curve shifts to the right, more particles now have sufficient energy for a successful collision. Okay. What about concentration? We know if I were to add in more particles into the same volume, I can end up with more collisions. I tend to demonstrate this with my pupils, where I'll have one pupil walking around the room. I'll then add in a second one and a third one, and it becomes harder and harder for them to avoid each other. Okay, I then demonstrate if I was to get other class loads of pupils into my classroom, there would be more collisions and therefore potentially more successful collisions. So if I were to increase the concentration, and we'll just do this one really quickly, but we can have a look. If I was to increase, again, let's say this is kinetic energy, this is number of particles, here's my activation energy. My original curve at one concentration would have this area under the curve. If I increase my number of particles, there are more particles. It doesn't shift left or right, but there are more particles, so I have a bigger curve, and therefore I have a greater area above the activation energy to the right of the activation energy. There are more particles represented by this area, and therefore more particles have sufficient energy. There is an increase in the rate of reaction. And that is why my temperature and my concentration, if they are increased, the rate of reaction will also increase, and vice versa. If they are decreased, then that rate of reaction will also decrease. So, having a look, we've looked at our temperature distribution diagrams and having a look at the effect that temperature or concentration have on our rate of reaction. We've not really considered the reaction as a whole and what's actually happening in there in terms of the energy. So we have this other diagram in higher chemistry that we call our reaction pathway, and the x-axis here is really just representing like how my reaction is moving forward. So this is like the start of my reaction moving to the end of my reaction. So if I just write reaction pathway here, okay, and here we're going to have something called enthalpy. So you should know enthalpy is the word we use for energy in chemistry. You know this from National 5. And what we're saying is all chemicals have some form of energy within them. They have chemical energy, and that will be a certain value. So there will be an enthalpy associated with my reactants, which I'm just going to write as R on here. My product that I make in the reaction will also have a specific energy. Now for this example, I'm going to put my P here, but I'm actually going to draw a second curve just to show you a different one. So this is my reaction pathway, and this is my enthalpy again. Okay, so again, if I just have my reactants here, but this time I'm going to say that my products actually have more, they're of greater energy to my reactants, and it's quite important here. So let's think about what happens in my reaction. Reactions don't just happen. Okay, I'm not just going to put in two chemicals and they're instantly going to react. Sometimes at room temperature that might be enough, but I'm not just going to have a line that runs straight down here, downhill, as if that's going to be energetically favourable. We've mentioned before that there's this activation energy that needs to be met. So what actually happens is my reactants need to be given enough energy to reach a certain point before that energy then drops to wherever the products are. Okay, so looking at this one here, this is going to go up so far to my activation energy and then drop to where my products are. Okay. There are different calculations that we need to do based on these reaction pathways. Firstly, I need to know the difference between this and this. So these values here, the difference here is my enthalpy change. Enthalpy is represented by an H. So my change in enthalpy tells me the overall change in reaction energy. And that equals the enthalpy of products minus the enthalpy of reactants. So let's assign this random values just now. Let's say here I'm at 25, here I'm at 50, maybe up at the peak of this, I'm up at 75. In order for this one here, for me to work out my enthalpy change, I would have the enthalpy of products, which I'm saying is 25, taking away the enthalpy of the reactants, which is 50, gives me negative 25, and the units we use are kilojoules per mole. That would be an enthalpy calculation. That would be how I would work out what my enthalpy change is. And note here that it is a negative value. My reactants have lost energy to become the products. They've given out energy. You should know from National 5 that an exothermic reaction gives out energy. So exothermic reactions have negative enthalpy values. Interesting. What about this one here? Let's give this a value of now 50. Let's say that this, remember we're working out our delta H, let's say that this is 75 now, and let's say the peak is at 100, say, okay? This time, my delta H is going to equal the enthalpy of the products, which was 75, take away the enthalpy of my reactants, which was 50, and that's going to give me a positive value of 25 kilojoules per mole. The positive is really important. We like writing that in. My reactants have gained energy to become the products. They've taken in energy. And you should know from National 5, hopefully you've maybe heard of it, that would be an endothermic reaction. An endothermic reaction will always have a positive value. Its curve will always have the products higher than the reactants. And the interesting part here is, what about this? Okay, we have to get all the way up this hill before that energy can come back down. I always think about if you have a little stick man here with a stone that he's trying to push up a hill, all of the energy goes in until you get to the peak of that hill, and then it's plain sailing all the way down. So let's have a look at one of these just a wee bit closer up and see what's happening in here. So I'll draw just a slightly bigger one for us to think about this. I'm going to have my reactants in here. I'm going to have an exothermic reaction. It's going to look like that. Okay, again, this is my reaction pathway. And here is my enthalpy. You can give me into trouble for not putting any units in my enthalpy on my axes. So I'm starting with my reactants here, and this is where I need to get to. This here is my activation energy. My activation energy is how much energy that I actually need to put in to my reaction to get to the top. So this change now is activation energy, which we've met already. So if I take the peak of that and take away the value that my reactants are, that will tell me the activation energy and the energy that is required by this particular reaction. That's the amount of energy to push that stone to the top of the hill before it falls back down. Okay. It's quite important that we're able to calculate this, and we can also do our enthalpy change. It's also important to note that some reactions are reversible. So you can go from the products and reform the reactants. So in that case, my activation energy would actually be from here to there instead of the reactants, because I'd be starting here. That would be my starting point. So wherever you're starting from to the peak is where you have your activation energy. And the reason that this happens, and if I just bring this in just now, the reason that this happens, if I am adding, say, bromine into this ethene molecule, this has to break, and this also has to break in order for these to go in. And there is a point where this is starting to break and the new bonds are starting to form, and it forms a really unstable intermediate. And that unstable intermediate, okay, so say unstable intermediate, and it doesn't exist for very long, that is called an activated complex. So I need my correct collision geometry and I need the correct energy, activation energy, in order to form this, which then allows the products to be formed. If this cannot form, then my products will not form. And that only forms at the top once it reaches that energy. So once all this activation energy is put in, that activated complex is formed, and then my products can be formed. Or vice versa, if I'm going backwards, my products start to break up, they go back to the activated complex, which allows the reactants to reform. Okay. The very last thing that I want to look at, just in terms of these diagrams, which I'll just put on the back of this one, again, if we look at this temperature distribution curve, when we add a catalyst, we know that that speeds up my chemical reaction. We've never discussed why. And the reason it actually speeds up our chemical reaction is not because it lowers this curve. It doesn't do anything like that in terms of this particular curve. This is a reaction pathway. We're going reactants to products, and it follows this path. What a catalyst does is it offers a second route to get to my product. And it does that by giving me a route that has a lower activation energy. So less energy is actually required by the particles to have a successful collision, because it's actually going a different way. Okay, it's like loading up Google Maps and being given two different options, one of which is going to cost lots of fuel in your car and the other one isn't. The catalyst route is the one that causes less fuel consumption, if you like, requires less energy by the particles, and so is a faster reaction. And so my curve would drop down. So you could be asked to sketch what the curve would look like if you used a catalyst, and you just sketch in a line underneath that showing that it would have a lower activation energy. Okay. So what you should be able to do using these diagrams is you should be able to work out your enthalpy changes, work out what the activation energy is, and also discuss what a catalyst actually does in terms of the energy required by the particles to have a successful collision. Just remember, if you have a negative delta H, you have an exothermic reaction, and if it's positive, then it is endothermic. So those types of calculations are really quite important for us to be able to do at higher chemistry. You need to be able to look at different examples, work out from the symbol whether it is exothermic or endothermic, and be able to do the calculation to determine the value. You need to be able to say, right, okay, well, here is my activation energy from here to there. That's going to be 75 minus 50, that's going to be 25. But you also need to be able to do this for the reverse reaction, so just be careful with that. That's about it, really, for our rates of reaction. The only thing I've not covered yet is our relative rate, which I maybe actually just do really very quickly. Relative rate of reaction is quite important. We've done average rate at National 5. We've always done the average rate of reaction, where you've done the change in quantity over change in time. That's our National 5 calculation. We now use a term called relative rate. And relative rate allows us to compare reactions as to how long it's taken those reactions to take place. And it's very easy, it is just 1 over T. And the units are going to be seconds to the minus 1, s to the minus 1. All I need you to do is understand that if a reaction takes 30 seconds to complete, then the relative rate is 1 over 30. And the units would be s to the minus 1. I'm just going to leave that as a fraction form just now, but you would put that into a decimal. S to the minus 1 would be your units. I've just put it in brackets just to remind you what the units are there. That's all it is. All we're looking for at higher level is for you to be able to do 1 over t and tell me what that relative rate is. Okay, you might be asked what the average rate, but that's not really a higher question anymore. It's more National 5, so quite important to think about. So that is everything for rates of reaction. It's quite a short topic. There's just a short summary. Really going through all the different points, and it's worth making sure that you understand those different diagrams and don't get the two confused. So thank you for watching, and I will see you next time.